Hi, this is Dr. John Bergduff. In this video, we are going to do a brief introduction to the concept of probability by looking at just some of the most fundamental concepts. Probability has a number of definitions that you have to learn and get used to, so we're going to do that first. And then we're going to, in this video, also talk about what's meant by empirical probability. So let's get started. First definition we have is random phenomenon, a phenomenon that has several possible outcomes that could occur. What are some examples of a random phenomenon? So some very common ones would be, for example, rolling a die. Little grammar lesson here. When you have more than one, you talk about dice. But if you only have one of them, it's called a die. That is a random phenomenon because each time you roll a die, you could get any one of the 6 numbers. You don't necessarily know which one you'll get each time, but it will be one of those 6. So that's a random phenomenon. Another example would be picking a card from a deck of cards. You don't know in advance which outcome you're going to get, but it's going to be one of the possible cards that you could get from a deck. Slightly different one would be looking at the genders of children in a 2-child family. Also random. You could get a boy and followed by a girl. You could get 2 boys. You could get a girl followed by a boy. You get 2 boys. So different possible outcomes there. Those are all called random phenomenon. These are in contrast to non-random phenomenon, like when you're in an algebra class and the instructor says solve for x, there's only going to be one outcome to that, one correct outcome, I should say. It's not that x is sometimes going to be 9 and sometimes it's going to be 11 and sometimes it's going to be 14. That would not be a random phenomenon. So random phenomena are a very special kind of thing. Here's some other definitions that have to do with probability. An outcome is one of the specific possible results of a random phenomenon. And the sample space is the set of all possible outcomes of a random phenomenon. So let's stick with that for just a second before looking at the idea of an event. Suppose you are rolling a die. If you're rolling a die, then your sample space, which we often represent with the letter S, would be the set of numbers 1, 2, 3, 4, 5, 6. It could be any of those. That would be the sample space, all possible outcomes. Now, if for some reason you're particularly interested in some of those outcomes, you call that collection of outcomes you're interested in an event. So maybe you're interested in, can I roll an even number? Well, the event, the outcomes you're interested in, if you want to roll an even number, are 2, 4, and 6. So the sample space is all possible outcomes. An event is a collection of outcomes you're particularly interested in. Let's do a few more examples. So suppose you are looking at the genders of the children in a 2-person family, 2-child family. For the sake of discussion, let's say that there's always a first child and a second child, even if they're twins, one of them came out first. So I can put the genders in an order. S represents the sample space, and I could have a boy followed by a boy. I could have a boy followed by a girl. I could have a girl followed by a boy, or I could have a girl followed by a girl. That's my sample space for the genders of 2 children. And maybe I'm particularly interested in, okay, which ones of those outcomes would result in both a boy and a girl? Well, there's 2 ways that could happen. Either the boy first and the girl second, or the girl second and the boy the girl first and the boy second. That would be a sample space and an event. Maybe your sample space is tossing a coin. In that case, or the outcome, the random phenomenon is tossing a coin. You could either get heads or tails. That's your sample space. And maybe your event is you're particularly interested in heads. So be a very, very small event, heads. Here's one that's a little bit more involved. Suppose your random phenomenon is drawing one card from a 52-card deck. The sample space then consists of all possible cards within the deck. And in case you're not terribly familiar with standard playing cards, here's a picture of all the standard playing cards in a deck. Notice that they are subdivided into suits. Clubs, diamonds, hearts, and spades are called suits. And within each suit, there are several different cards. We start with an ace, which has 1. And then we have 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king, which have pictures on them. They're sometimes generally called face cards. This would be the entire sample space. If you're interested in the event of drawing a face card, I'm just going to circle those here. That would be any one of these outcomes. A jack, a queen, or a king in either clubs, diamonds, hearts, or spades. That's the event of drawing a face card. If I'm looking at the event of drawing a 7 or a club, well, here's all my 7s. 7 of clubs, 7 of diamonds, 7 of hearts, 7 of spades. Here are all my clubs. Ace, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. And my event F would therefore be anything that I have circled in either of those circles, either the horizontal one or the vertical. Take all of those all together. So, a little bit more complicated sample space, a little bit more complicated events. Here's another one. Consider the idea of rolling 2 dice. So that would be dice. The sample space is shown here in the middle. Let's just say for discussion that one of the dice is gray and the other one's white. Here is every possible outcome you could have. For example, this one represents rolling a 3 on the gray die and a 2 on the white die. This is the whole sample space. If I were interested in counting all the outcomes in the sample space, I see that there are 6 columns, and in each column there are 6 rows. So 6 times 6, there's 36 total possible outcomes. Now suppose in this particular example, you're looking at event E. When rolling 2 dice, rolling a sum of 8. Identifying that event is simply looking at the sample space and figuring out which 2 dice roll would give me a sum of 8. 6 and 2 would do it, for example, but so would 3 and 5, and 4 and 4, and 3 and 5, and 2 and 6. I'm going to just circle these. Any one of these outcomes that I've circled in red would give me a sum of 8 on the 2 dice. Let's look at example F. I'm going to clean that off. When rolling 2 dice, rolling an even on the first dice. So we're just going to circle. We'll say that the gray die comes first. Let's circle all the outcomes where the first die, and I should say die, is even. All of these are, all of these are, all of these are, That's my event F. All of these outcomes, in all of these outcomes, the first die is even. Now when I look at that versus the example we did right before it, which I'll put right back up there in a second, there seem to be a lot more outcomes that give me a rolling an even on the first die than there was on rolling a sum of 8. That, again, was these guys. There's just not that many outcomes that result in a sum of 8 by comparison. So I have a feeling that maybe event F is a little bit more likely than event E, and that actually gets right at the heart of what we mean by probability. Probability assigns a number that indicates how likely a specific event is to occur. That number is called the probability. So because I think event F, the green one, is more likely than event E, the red one, the probability of event F should be some higher number. How do we figure out what kind of number to associate with that sense of likelihood? There are 2 ways to do so. In this video, we're going to look at one, and then I have another video to look at the other one. So the most simple way, perhaps, of ascertaining what the likelihood of a particular event is to look at something called empirical probability. In empirical probability, basically what you do is you conduct an experiment. You repeat the phenomenon over and over and over again, and you observe what happens and keep a record of it too. The empirical probability is defined this way. Suppose an event is repeated, an experiment is repeated n times, and an event you're interested in occurs r times. The empirical or experimental probability of that event is given by P of E. That's going to be read as probability of event E equals R, the number of times the event occurs, over N, the total number of experiments that you ran. For example, that was a bad slide, sorry. Suppose you have a die and you think it possibly is loaded, and you're interested in the probability of rolling an even number, much like we talked about before. Because you're not sure, what you do is you take that die and you roll it 35 times, and you keep track of the outcomes. The outcomes are the numbers from 1 through 6. Frequency is a count of how often each one of those outcomes occurred when you roll the die over and over and over again. So, for example, the number 1 came up 5 times, but the number 4 came up 7 times. What is the probability of rolling an even number? So the formula was R over N. R is the number of times your particular event occurred. So we're interested in rolling an even number. That would be here, here, and here. The number of times that you got an even number would be 9 plus 7 plus 5. 9 plus 7 plus 5. The number on the bottom is the total number of times you repeated the experiment. How many times did you roll the dice? That's going to be 35. Now, you add this up. 9 plus 7 is 16, plus 5 is 21. So the empirical probability is 21 over 35. Should you reduce fractions? Yeah, we'll just take that as sort of an unwritten rule no matter what. Notice that 7 divides into both 21 and 35. 7 goes into 21 3 times. 7 goes into 35 5 times. The probability on this die of rolling an even number is 3/5. Now that's a little bit more than half. So you might actually be suspicious that something weird is going on, because I think, just sort of logically, if you rolled a die, it seems like the evens and the odds should come up about the same number of times. 3/5 of the times you got an even, so that's a little bit more than half. So there might really be something wrong here. A classic situation where you need to apply empirical probability is with human behavior of any kind. Human behavior is somewhat irregular, and therefore really what you have to do is run an experiment. So let's say there's an election coming up, and I want to know who's going to win, or what the probability is that they're going to win. Well, of course, I could wait for the election to happen and then I'll know, but I really want to have a clue about it now. So what I decide to do is, out of all the people who could be voting, I select 1,000 people and I ask them who they think they would like to vote for. Let's say the candidates' names are Smith, Gwynn, and Gutierrez. And I'm interested in the probability that Gutierrez will win. Well, the R in this case, the experiment is asking all the questions. The R is the number of times that somebody said that they were going to vote for Gutierrez. 365. 365 people said they'd vote for him. Out of the total number of experiments, the experiments then are basically, each time you ask a person, that's an experiment. There's 1,000 people that you asked, 365 over 1,000. And when the numbers become large and cumbersome, rather than reducing the fractions, which can be a little bit messy, I'd have to look for common denominators, we also are sometimes pretty content to just say, let's figure that out as a decimal. Just divide 365 by 1,000, and the probability is 0.365. This is called empirical probability. And it is a simple, basic way to determine probability, but we're going to find out in another video that if you happen to know something special, you can figure out probabilities without having to run experiments. So stay tuned.